welcome back. My name is Isaac, and today I'd like to do a short video on Galilean relativity, which is not the most modern physics of relativity, the most modern special relativity, but this works really well for most things that we would see in the natural world. So, for example, let's say that it's raining out. This is a common problem. So here's the road, and let's say that it's raining, and the rain is coming vertically downwards at some velocity. And let's say that we don't know that velocity, so the velocity of the rain with respect to Earth, so I do the velocity of the rain with respect to Earth, so V sub RE. That's going to give us kind of what frame we're in. And then we have, let's say that we're driving a car, and we're driving it at some speed with respect to Earth. So let's say that we're driving at the velocity of the car with respect to Earth, or V sub CE, is going to be equal to, let's say, 50 meters per second. And we don't know the velocity of the rain with respect to Earth. But let's change reference frames now. So instead of viewing this from the Earth's reference frame, let's view it from the car's reference frame. Alright, so from the car's reference frame, the car can claim that it is standing still. And this is the whole point of Galilean relativity, is anything at a fixed velocity can claim it's standing still. Because you'll notice that if you're driving, that you only feel a force if there's an acceleration. So once you're cruising on the highway, you could throw a ball up in the air, and the ball would drop straight back down in your hand. So unless there's an acceleration, there's no way to tell who is really moving, and therefore everybody can claim they're not moving. Now, if the car claims he is not moving, he will claim the rain is moving towards him at a speed in the x direction of 55 miles per hour. And we've all seen this before, so now the rain is coming down at an angle with respect to the driver of the car. And let's say that we're given that angle with the horizon, and that angle is theta. We'll say it's 50 degrees. Alright, now here's the question. We don't know the velocity of the rain with respect to Earth, but we do know the velocity of the car with respect to Earth. And if the car claims it is standing still, then the car will claim that the x velocity of the rain is in fact 50 meters per second. So here is the velocity of the rain with respect to the car, or V sub RC, for rain with respect to car. And this is the x component, and we know that must be equal to 55 meters per second. It's the same reason, like for example, if I and a car are driving at each other at 25 miles an hour, I could claim that my car is standing still and that car is coming at me at 50 miles an hour, which is the 25 plus the 25. So if the car claims it's standing still, even though it's moving 50 meters per second, then the rain must be moving towards it in the x direction at 55 meters per second. Now we have some vector velocity of rain with respect to the Earth, and the car is not going to disagree on this velocity with respect to Earth. So that's going to be the same velocity. The reason why is because the car is not moving in the y direction, right? The car is only moving in the x direction. So it will agree with Earth about the y direction velocities, but not the x direction velocities. And so you'll see that there's going to be this final vector here. This is going to be the hypotenuse of a right triangle of vectors. And this is going to represent the velocity of the rain with respect to the car. So in other words, we're back in this reference frame where the rain's coming down at an angle of 50 degrees. So this is how you set up one of these Galilean relativity problems. Is you think about in what ways do the moving reference frames agree with the Earth's reference frame? And in what ways does the reference frame you're interested in disagree with the reference frame of Earth? And so you're usually going to find with a two-system problem, two systems meaning rain and car, we're not going to count the Earth because that's kind of our static reference point. And so with a two-system problem like this, you're going to end up with two smaller vectors and one summation of vectors. And if we don't know, so we don't know velocity of the rain with respect to Earth, we don't know the velocity of the rain with respect to the car. But we do know the velocity of the rain with respect to the, I'm sorry, this is the velocity of the rain with respect to the car in the x direction. This is the total rain with respect to the car. So because we don't know this or that, but we do know the x component of VRC and the angle that it makes with the horizon, 50 degrees, we can use trigonometry to solve. And so, for example, if we wanted to figure out the total velocity of the rain with respect to the car, we know that if we want to relate hypotenuse with adjacent and an angle, that's cosine. So cosine of 50 degrees is going to equal the adjacent, which is 55 meters per second. Or, I'm sorry, 50 meters per second is what we originally said. 50 meters per second with the hypotenuse, which is what we're solving for. The total velocity of the rain with respect to the car. So we can move things around and find that the velocity of the rain with respect to the car is equal to 50 divided cosine 50 degrees. And that is approximately equal to 77.8 meters per second. And this number makes sense because we're looking at the longer side of the triangle. We're looking at the hypotenuse. So this had better be bigger than just the x component of the same thing. And so we've now solved for VRC to be 77.8 meters per second. And now we can solve similarly for VRE, the velocity of the rain with respect to Earth, by using a similar trigonometric relation. This time it's we're relating opposite with adjacent or opposite with hypotenuse. So you can use tangent or sine. Let's go ahead and use tangent. So tangent of theta is equal to opposite, which is velocity of the rain with respect to Earth, over adjacent, or velocity of the rain with respect to the car, the x component, which is 50. And we know theta is 50 degrees. And so, just like that, we can multiply the 50 over. Tangent of 50 times 50. So v, the velocity of the rain with respect to the Earth, is 59.6 meters per second. And so this is how we break these problems into components. The reason why it's a little bit harder in two dimensions, so just as a quick example, in one dimension we typically don't have a problem with this. Like, for example, let's say I have a person that is standing still right here, and then there's like a train track, and there's this train cart that's moving in this direction with some velocity 1. And then let's say that we have a person on the cart who is walking with a velocity with respect to the cart. So in other words, a v2. So if the cart's moving at 5 meters per second with respect to Earth, and the person on the cart is moving at 2 meters per second with respect to the cart, and we want to know how fast is the person moving with respect to the stationary observer, well, we would just take the velocity of the cart with respect to Earth plus the velocity of the person with respect to the cart. So this would be velocity of the person with respect to the cart velocity of the cart with respect to Earth, and we would just sum the vectors together to get the velocity of the person with respect to, let's say, Earth. Earth being the stationary point. So vector addition, though, in this case is simple because all of our vectors lie along the same axis. So this is in one dimension, right? The reason why 2 dimensions and 3 dimensions gets a little weird is because of the vector addition aspect. In 2 dimensions, we have to add our y components separately from our x components. But in the way you think about these problems, there's not a whole lot of difference between 1 dimension and 2. It's just harder to visualize 2 dimensions. So my recommendations is always just think about different parts of the problem from different reference frames, like whether that reference frame is the reference frame of the cart or the reference frame of the person with respect to the cart. So think about these problems and stop. Draw a picture in each reference frame even. So like, for example, let's say that the cart is standing still now. Well, the cart would see that this person right here would be walking this direction with that velocity of 2 meters per second. But we know that the cart's moving at 5 meters per second, so in the cart's reference frame, it's going to look like the stationary observer is actually walking away at 5 meters per second. And you'll notice that the laws of physics here are the same, because if we ask what the velocity of this person is with respect to this person, we still get the 5 plus 2 equals 7. And so, these problems can be challenging. I still struggle setting them up. But just remember, they'll usually reduce to right triangles, or at the very minimum, some sort of non-right triangle that you can work with. So remember, there's going to be usually one velocity that's the hypotenuse, and then 2 that are the opposite and adjacent. So I hope this was helpful. Sorry for the glare on the screen and for sitting down. It's a little awkward here, so thank you.